Let's continue this discussion now about deep learning for earth system science, but more specifically about hybrid models. And we are still discussing based on figure 4, but we'll move to figure 3. We'll move to figure 4 for a bit more of this idea. Some of the concepts in figure 3 have already been adopted in a broad sense. For instance, linkage 3 relates to model benchmarking and statistical downscaling and model output statistics. Here we argue that adopting a deep learning approach will strongly improve the use of spatio-temporal context information for modification of model output, so post-processing in some ways. Emulation has been widely adopted in several branches of engineering and geoscience, mainly for the sake of efficient modeling, but tractability issues have not yet been explored in depth. Other paths such as the hybrid modeling, linkage 2, where you try to replace a submodel with AI, appear to be much less explored. Conceptually, the hybrid approaches discussed above can be interpreted as deepening a neural network to make it more physically realistic, where the physical models come on top of a neural network layers, which we'll see in the next figure. It contrasts with the reverse approach discussed above, where the physical model output is produced and then corrected using additional layers of machine learning approaches. We believe that it is worthwhile pursuing both avenues of integrating physical modeling and machine learning. Okay, so figure 3 then presents a system modeling view that seeks to integrate machine learning into a system model. As an alternative perspective, system knowledge can be integrated into a machine learning framework, and this may include design of the network architecture, physical constraints in the cost function for optimization, or the expansion of training datasets for undersampled domains, that is physically based data augmentation. Right? Imagine you have sampling limitations, but AI/ML can help you overcome some of this with physically based data augmentation. For instance, while usually a so-called cost function like ordinary least squares penalizes the model data mismatch, it can be modified to also avoid physically implausible predictions for lake temperature modeling. So this we already said before here, so I'm just going to read that in this context a little bit. So the notion this notion is also related to the direction of attaining explainable and interpretable machine learning models, as we said before. So what is figure 4 then? Its interpretation of hybrid modeling as deepening a deep learning architecture by adding one or several physical layers after the multi-layer neural network to make the model more physically realistic. If you don't understand that, don't worry about it. Basically, we are blending physical model with deep learning to improve the model itself. Okay, it's different than optimizing just parameters or replacing a submodel. This is like a coupling between the two. So here the multi-layer neural network with n number of layers of n number of neural layers and m number of physical layers. Okay, so here is the model input, simple features, so learned mapping 1, learned mapping 2 to n plus 1. More abstract features, so you have n number of neural layers here, then comes learned mapping n plus 2, then you have m layers of physical layers, m physical layers, and then you have the physical model receiving this information to produce the physical output. So a lot of reprocessing and physical interpretation or pattern recognition, let's say in simple words, has happened to provide input to the physical model, which then is expected to give more accurate physical output in some simple way, if you can imagine it. Okay, what's happening here? We are again looking at input, two examples of how these things can work. Input of past temperature trends. There is some deep learning approach, deconvolutional neural network without worrying about what they are. We're producing some motion field. So this is the physical warping model that is going to get this input. It can get it directly from the it can get input directly as past input temperatures, which it is designed to take and provide you predicted future temperature field. But can you blend it with a machine learning model in the middle, where you take the same temperatures, you can give the temperatures directly to the physical warping model, and you can run it through convolutional devolutional neural network, create a motion field which is going to improve your physical interpretation to the physical warping model, and then improve the predicted temperature field. These are just examples, and here is another good example. You are taking temperature, radiation, and precipitation, which are very important for very important as inputs to sequence and time series of drivers to produce predicted transpiration and photosynthesis. It can translate into net primary production and crop yields and various other downstream products, let's say. So you start from here, photosynthesis. There is predicted transpiration and photosynthesis that is coming in as input. It's taking an input sequence and time series of drivers. These are then fed to N. So this is RNN here, which is the I should have remembered it. I read it, and then I forgot it. So let's just look it up quickly. So let me say it, and then we'll here it is. Recurrent neural network. Why I didn't bother to remember it is because it's right there. So it kind of iterates over these n recurrent neural net layers, and then produces a sequence of stomatal aperture, and then physical diffusion and energy balance model takes it and produces transpiration. So you have this kind of a loop here, and basically you are again taking the combination of data here. Here only temperature was involved. You have multiple inputs. You can't easily see the relation between them in simple statistical models, and then they go into a physical model, energy balance diffusion model, and then they produce an output based on some empirical relation between these that you have used. But can you improve that by using a recurrent neural network? And sequence of stomatal aperture, basically stomata are opening to capture CO2, and their goal is to open long enough to capture enough CO2 for photosynthesis, but not lose too much of the water vapor or water they have brought up with hard work from the root system. So you want to open, you will lose some water as transpiration, but you want to capture CO2 and close as soon as possible. And then there are issues to worry about. What happens if CO2 keeps increasing in the atmosphere? What happens to the so-called stomatal conductance, which is the opening and closing, and so on and so forth. So if you want to read it, a biological regulation process, opening of the stomatal valves controlling water vapor flux from the leaves, is modeled with a recurrent neural network. Then a physical diffusion model is used to estimate transpiration, which in turn influences some of the drivers such as soil moisture. The basic scheme is inspired by this paper that it talks about. Recent advances in two fields of methodological approaches have potential in facilitating the fusion of machine learning and physical models in a sound way, and probabilistic programming and differential programming are the two that you want to merge here. Probabilistic programming allows for accounting of various uncertainty aspects in a formal but flexible way. A proper accounting for data and model uncertainty, along with integration of knowledge by prior and constraints, is critical for optimally combining the data-driven and theory-driven paradigms, including logical rules as done in statistical relational learning. In addition, error propagation is conceptually seamless, facilitating well-founded uncertainty margins for model output. This capability is largely missing so far, but is crucial for scientific purposes and in particular for management or policy decisions. Differentiable programming allows for efficient optimization owing to automated differentiation. Technical. So let's just walk through it. This helps in making the large, nonlinear and complex inversion problems computationally more tractable, and in addition allows for explicit sensitivity assessment, thus aiding interpretability. Basically, when you say complex inversion problems, nonlinear complex inversion problems, every time you have data and you are doing deep learning and trying to get a data-driven model, let's say, or if you are doing data assimilation and trying to blend models with data, which is another way of thinking about this, then there is always large inversion operators involved, but in this case it doesn't have to be real physical matrix inversion, but you know that you are dealing with lots of data in these recurrent neural network type or convolutional devolutional neural network and so on. So large data, petabytes of it, obviously brings lots of these challenges. We'll come back and look at advancing science and conclusions in the next podcast, because this one is already 11 and a half minutes. It'll get a little too long if I continue with this. Okay.